You're like my husband, though. You know what I'm saying? And like we go places, it's like here's Steve, and
You're like everybody's husband. Like everybody wants to marry you. Every woman, every guy, everybody. It's like Kyle's my husband. It's like polyamory to the nth degree.
The person that called me a gnome, a discount garden gnome,
yeah, fuck him
to marry me. Yeah. So
that was
okay,
me.
Shannon.
Discount garden gnome.
Shannon, I'm handing the reins to you, and we will kick it off.
All right. I expect a fair fight. Nobody talk over each other. Okay, we both know that both of you have presentations this evening, and we agreed beforehand that Steve was going to go first. So we are going to start the presentation portion. So everybody will have a moment or the time that they require to go through their presentation, and then we're going to have some just free-form discussion. Does that sound agreeable to both of you?
Sounds good.
All right. Okay, all right. Dave, do you mind transitioning the screen and putting on Steve's presentation, please and thank you? All right, Steve, the floor is yours. Don't make me mad.
I'll try not to. Just so people know, my slides got corrupted. I had some errors in this particular presentation. I will correct them as we go. But unfortunately, this was a PDF file that I had saved, and it's the only copy I have left, so I have to use this particular copy. So there are some mistakes, but I'll go through them. And so getting into this discussion, I wanted to have some objectives at first, and to clarify that both John and I have talked about this for a long time over the last couple of weeks, and we both agree that the question DNA is a code is formed because the DNA molecule, we both agree, is not a code. I think, but there are people out there that think it is. So I think it's a valid question to them, but to John and I, like, no, it's not a code. Oh, so anyways, our objectives. Explain the very basics of the central dogma of biology, which is the DNA to mRNA to proteins, which John is going to do as well. I think we're going to have exactly the same presentation as far as that. I want to show that DNA itself is not a code, especially a true code, but a macromolecule that stores biological information, and that there's a difference between a code and a cipher. And I skip the next slide because that was an error, and then go right to the next one. There we go. Thank you. My arguments will be basically that DNA itself is not a code; it's a macromolecule. Which, again, I can't change that, but we agreed that it's not. So that one's kind of no longer applicable. But the genetic code is a misnomer, and that is an analogy for a heuristic approach to understanding concepts. It is more aptly akin to a cipher than a code. And I'll be explaining the differences between a code and a cipher and why it tends to be more of a cipher than a code, but it's kind of pseudo of both depending on how you use the terminology, whether you're coming from cryptography or you're coming from information theory or whatever from biology. The words mean different things to different people, and I've talked to many different people, and specialists and experts in one field say it is, other ones say it's not. So I think it depends on what your area of expertise is. Next. What is DNA? DNA is deoxyribonucleic acid. It's a macromolecule. Most people have had some biology, so this is kind of review for them. It has 4 nucleotides that it's comprised of, with a sugar phosphate backbone. It's read by what's called RNA polymerase. What a little enzyme comes on, and it basically will attach to and as it does, it produces an mRNA strand, which is messenger RNA. Next slide. This is called the process of transcription. The central dogma of biology is basically DNA through transcription will go to mRNA. mRNA will go to a ribosome, and then it'll be translated into a protein. The way this works, again, is this RNA polymerase will read the DNA, and as it does, it produces an mRNA strand. That mRNA strand then goes through a little thing in the cell nucleus that'll go to the ribosome. The ribosome will have a process by which it translates it, and it forms what's called a polypeptide chain. This chain will also be called a protein if it's over a certain amount of amino acids. Next slides. Okay. The relationship to RNA and DNA, besides a different sugar base, is that the RNA is a complement to the DNA strand with some exceptions. The T will be coded for A, the A will be coded for U, which is uracil instead of thymine. C will code to G, G will code to C. Again, I'm doing this real quickly, and this is very basic. If people want to get more technical about this, we can do that later on. But this is just kind of more of a review for the people that have had biology. The 3 RNA base pairs translates into a specific amino acid. This is called a nucleotide triplet. So each of those three things, like AUG, will code for a specific thing. And that we'll look at a chart and see what they will code for. And I'm using that code in this particular case as an analogy because that's just how we communicate a concept. Next slide. The mRNA to protein process in the ribosome works by this. You have what's called a tRNA or transfer RNA that has an anticodon and an amino acid attached to it. The specific three letters will code for a very specific amino acid, and as that chain that you see at the very top grows, it's a growing peptide chain, each amino acid will be added one by one. The proteins will be comprised of either one peptide chain or multiple peptide chains, and a peptide chain is really just a group of amino acids that's been put together through peptide bonds. Next. The way that the tRNA codes for this, and I was going to change this, so this is one of the mistakes I made. It's not really tRNA is encoded for. It's that tRNA is produced through a non-coding process because it's part of non-coding RNA. So the way this basically works, people have asked me before, why do we have a very specific tRNA with a very specific code on, nuclear amino acid on it? And the reason being is because you have this enzyme called aminoacyl tRNA synthase. This particular one is specific for methionine. What happens is you have a tRNA for methionine that will fit exactly in that enzyme. You have the methionine amino acid that goes on the top, and then ATP, which is the energy molecule, is used to fuse them together, and that produces AMP, which is adenosine monophosphate plus two phosphate atoms. So it breaks apart a bond that releases energy, and it charges that tRNA. So now it's tRNA met, and that's what it'll take out of the cell nucleus to put in the ribosome to cause that chain, because all these things are floating around. So it'll pull that one out, and that's what it'll bond to it based upon the codon. Next. So this is not an RNA synthesis chart. This was a mistake that I made. I don't know why I called it the RNA synthesis chart. It's not. It's just a codon chart. So the way this works is pretty simple. There are three letters in the triplet. If the first letter is U, you go to the first thing. If it's A is the next one, for the second letter, which is the column, and then you look at the row for the third letter. And if you notice on here, certain things will only code for one particular amino acid. If you look at UGG, that'll only code for tryptophan. However, things like proline will be many different things will code for it. CC, anything. CCC, CCA, CCG, CCU. Those are all code for proline. That's called third base wobble. And that's going to be critical to why this is not a code. And yes, I know that I'm going through this very quickly because I want to get to the code portion, because I think that's what's the main I think so far everything John's going to agree with me on. John, real quick, is there anything that you want to touch on real quick, that just on the biology stuff?
No.
I agree so far.
No.
Okay.
I mean, this chart here, this set of rules is what people typically call the genetic code. But
okay, awesome. All right. So what is a code? A code is usually a cryptic substitution system that's decided on two or more people, called the sender and receiver. Codes are secondary symbols that represent a primary symbol. For example, the car is fast. CAR could stand for, quote, nuclear weapon, and fast, quote, for ready for launch. This way, if a third party intercepted that coded message, they would need what's called a code book to understand what the secondary symbols represent. So in this particular case, a true code is a one-to-one correspondence. If you have a word, you have something else that it represents, you have a separate symbol. So that symbol of nuclear weapon, right, think of it as one object, represents the one object car. So if people were, the other way around, the car would represent the nuclear weapon. So we had an enemy, right, that intercepted this message, and they got the message, car is fast. They wouldn't know what it means unless they had the code book to translate that it was car represents nuclear weapon and fast meant ready to launch. That's what is a true code. So the symbol is what is the code. And next slide. Oh, I'm sorry. Am I one slide ahead? Because I forgot to tell you to. There you go. The genetic code if we assign primary symbols to the nucleotides in the DNA by labeling them, right? If I tell somebody ahead of time, if I want adenine, thymine, cytosine, and guanine to be represented by a secondary system, a secondary code, then I will say A, T, C, and G is the code. That is the code that represents those specific nucleotides. Those are arbitrary. I could be use anything, right? I pick anything I want, but it just so happens that I think the first letter's very basic way to code for those particular nucleotides. So that seems trivial to me. I don't think that's what really is implied when somebody says DNA is a code, because I do agree that A, T, C, and G, those symbols are a code because they're secondary symbols representing the primary symbols, the secondary being A, T, C, and G, the primary being adenine, thymine, cytosine, and guanine, and the words themselves, not just the ontological, meaning in existence, nucleotides in the DNA. Next. The word code is polysemous, meaning it has multiple different meanings, and that's one of the problems when people say, is DNA code? It really means, what do you mean by code? What are you looking at it from? Obviously, is it a program language? Well, no, DNA is not a program language, but they use the word code in programming language, and the reason why is because in a programming language you have some instruction that is the secondary symbol that executes something by representing a primary symbol or string. For example, J and Z in assembly language means jump short if not zero. You have different flags in a computer, as people may know. One of them is called the zero flag. If that happens to be zero, then you'll jump to some other memory location or some other part of the code. And J and Z is a code because it's coded by somebody that's performed a specific action to jump, if not zero, if a condition is met. That is a programming language or code. Next. So what is a cipher, though? Well, a cipher works on a little bit different principle. Cipher works generally, you encrypt or decrypt by use of an algorithm. Not always, not necessarily. It depends on what you mean by cipher. But unlike the need for a code book where you have a word or phrase representing another word, ciphers work on a more bit-by-bit system. It works on one letter at a time, and it can be easily deciphered if you know the algorithm. For example, if I wanted to decipher a phrase, the nuclear weapon is ready to launch, I could use a Caesar shift by shifting each letter one to the right on the alphabet, resulting in, well, what you see there, because I'm not going to be able to pronounce it. But that would be a cipher, because all I have to do to know how to decipher that is know how it was originally ciphered and used as deciphering algorithm, which would in this case be shift it one to the left. Next slide. So in order to cipher that string, I just have to know the deciphering algorithm, what's called the key of the cipher, or the Caesar shift. In this case, be one letter to the left to get back to the original encrypted message. I could do that with any kind of encryption. As long as I have the key, I could decipher the original message. And a fun fact is there's something called a Vermin cipher, which is unbreakable so long as you know the rules of the cipher are followed. They're called a one-time pad, based upon Shannon's communication theory of secrecy systems, which I think John's going to get into a little bit, which is one of the reasons I mentioned it here. Next. So why isn't DNA code? Well, obviously we've already established DNA is a macromolecule. So when they say DNA is a code, that as itself is clearly a not true statement. DNA itself as the molecule is not a code. But I think John and I both realize that that's not really the question at hand. Because he agrees, saying DNA is a code is sure. Yeah.
Do you mind if I explain why DNA itself is not a code, just real quick?
Absolutely, go for it.
So the pages in a book can carry a message with ink on that page, but the page itself, just ink and paper is not a message. And DNA can carry messages, but DNA itself is not a message. So there's vast amounts of DNA in our genome that's not used to carry any sort of encoded message. So that's why DNA itself is not a code. It's just the material that the messages are written in.
Same thing like your hard drive is not a code. The information on it is different from the hard drive, right? So like you said, it's saying a book is a code rather than the information compiled in it, right? So we both agree that that is not the code. I do believe that the genetic code of ATGC is a code where you're representing letters, which is your secondary symbology, represents a specific type of nucleotide. So A, T, C, and G, those letters are a genetic code. And I think that's when they talk about the genetic code, that's what they're specifically referring to as an information. But the information itself is more of a cipher than a code. Next slide, and I'll explain why. So why isn't DNA not a code? One could use a codon chart to determine